Geeks Cocktail. Part 1. Mix Principles, Diffusion, Convection, Turbulence. In this video, the mix principle, diffusion, and convection, and turbulence are explained with experiments. Many cocktail books and cocktail-related sites explain the purpose of the shake. The three purposes of the shake are to mix, to chill, and to aerate. Then, after explaining the purpose of the shake, an explanation of how to shake the shaker is given. After explaining that there are 1,000 different ways to shake the shaker depending on the bartender, an explanation of typical shaking techniques is given, including the two-step shake and the figure-8 shake. Additional explanations such as the importance of using the snap when shaking the shaker are also usually given. However, it is rarely explained why the shaking of the shaker achieves the objectives of mix, chill, and aerate. Also, the effect of shaking the shaker on the movement of the ice and liquid inside the shaker is not explained, and it is only stated that shaking the shaker in this way causes complicated movement inside the shaker. Essentially, the physical and chemical principles for achieving the purpose of the shake are explained, and then it is necessary to consider the movement of ice and liquid inside the shaker, which is optimal for practicing the principle. In this video, the principles for one of the objectives of the shake, mix, are explained. To mix is to bring different things into a state of uniform dispersion. The screen is an image diagram of mix. The left side of the screen shows the separated state before mixing, and the right side of the screen shows the state of uniform dispersion of different materials after mixing. Diffusion and convection are necessary for mixing. Diffusion mixes by interchanging different substances at the molecular level, but it takes a significant amount of time for them to mix completely. Convection quickly increases the interface between different things by stretching the separated state with flow. Convection includes natural convection generated by temperature difference and specific gravity difference, and forced convection generated by external force. In order to achieve the goal of mix and shaking, it is important to generate forced convection by an external force such as shaking the shaker. Diffusion, one of the effects of mixing, is the interchange at the molecular level at the interface between different materials. Convection, another action of mixing, stretches the mass of different materials by flow, thereby increasing the size of the boundary surface compared to the separated state. Convection increases the size of the boundary surface, which in turn increases the molecular level interchange of different materials at the boundary surface due to diffusion that occurs at the boundary surface. This is why convection is so important for mixing different materials quickly. We will try an experiment to confirm the difference in mixing due to convection. The glass is filled with a chili pepper to make it easier to see the flow of the liquid. The left side of the screen shows mixing by the action of forced convection and diffusion. The right side of the image shows mixing by natural convection and diffusion. There does not seem to be a significant difference in the mixing speed between natural convection and forced convection. Why is this? In fact, there are two states of flow, laminar and turbulent. Laminar is a flow in which the fluid is in regular motion, while turbulent is a troubled flow in which the fluid is in irregular motion. In order to mix liquids, a state of turbulence is necessary in which adjacent parts mix together due to irregular motion. When an obstacle is present in a laminar flow, which is a regular flow, turbulence is generated behind the obstacle. The higher the velocity of the flow, the more turbulence is generated. Turbulence consists of vortices of various sizes. Each of these vortices, large or small, causes a switching of elements due to diffusion, so that adjacent parts mix together. However, the lifespan of these vortices is short and they disappear quickly. In the previous experiment, there was no difference in the rate of mixing between natural and forced convection. This is due to the disappearance of the turbulent vortex. Let us confirm the difference in mixing due to turbulence in the experiment. Unlike convection experiment 1, the glass on the turbulent side is stirred with a muddler after the food coloring is added. Since the muddler itself becomes an obstacle in the flow, turbulence is generated behind the muddler. This turbulence causes the food coloring to mix more quickly than in the previous experiment. In this video, we explained the principle of mixing. It explained that mixing requires forced convection to stretch the boundary surfaces of different elements, the generation of turbulence that turns the flow of forced convection into a flow of easily mixable conditions, and the action of diffusion, which is the replacement of elements in vortices of various sizes in the turbulence. As a large vortex of forced convection, this series of actions can be repeated to achieve efficient mix. In shaking, the ice inside the shaker and the strainer of a 3-piece shaker are the obstacles to generate turbulence. I find it difficult to have a concrete image of increasing the velocity of forced convection inside the shaker. I plan to explain these things in detail in another video, but I'll touch on them briefly in this video as well. A high flow velocity means that the flow distance is long in 1 second. There are two ways to increase the flow velocity inside a fixed size shaker. One is to increase the speed at which the shaker is shaken, and the other is to increase the actual distance traveled inside the shaker. In other words, forced convection, which causes rotation along the inside of the shaker, and increasing that rotation leads to higher velocities. The next video will cover the chill principle, heat conduction, and convective heat transfer. The explanation will include experiments using thermo-ink, which changes color with temperature, and thermography, which produces images of heat distribution. If you are interested, please subscribe to the channel and watch.